All right, now we need to learn how to take the derivative of a couple more functions. In particular, we want to learn how to take the derivative of y equal log base a of x. Need to take the derivative of a logarithmic function. I want to do this with it being log base a, because that's doing it in its most generic form. And then after that, we can get specific. All right, now, since we obviously don't know how to take the derivative of a log yet, I want to convert this to something that we do know how to take the derivative of. In other words, I'm going to take the logarithmic expression and rewrite it as an exponential. So rewriting this in exponential form tells us that a to the y is equal to x. That is the exponential version of that expression. And again, I write it that way because we know how to take the derivative of exponentials. So differentiating this side with respect to x, and oops, didn't leave myself enough room. Let me create some more space. Differentiating this side with respect to x. The right side is the easy one. Derivative of x is 1. Derivative of an exponential always gives us back the exponential, which was the a to the y, times, we're going to have in here also a natural log of an a, because as we said in previous videos, of a change of base type scenario. And by the chain rule, we're going to have a y prime. All right. So solving for y prime, this gives us that y prime is equal to 1 over a to the y times natural log of a. All right. So a to the y, again, what is a to the y? Well, in our previous statement that I've sort of written over now, in our previous statement, we said a to the y is just x. So to simplify this expression, I can make this 1 over x times the natural log of a. And that is the derivative in general of a general logarithm base a. All right. Now, specifically, if we wanted to look at y equal natural log of x, we wanted to look at that one in particular, then we could take this previous result and say, well, okay, what would that tell us about y prime? Well, this result says it's going to be a 1 over x, x on the bottom, and also natural log of a, but this time the a, which is the base, is an e. So we have a natural log of e. Well, natural log of e is 1. So therefore, our y prime for our natural log function just turns out to be a 1 over x. With this same procedure, we could generally say that if y equals natural log of u, with understanding that u is a function of x, then y prime is going to be a 1 over u times a u prime. And again, that's just going to be the chain rule. All right, so for something like, if we had y equal natural log of sine of x, applying that result would tell us that y prime would be 1 over sine of x. Right, that's for the natural log part. Moving inside, derivative of sine is cosine of x. And moving, technically speaking, moving inside one more time, derivative of x is 1. And we'll probably get to the point where we can abandon that 1. But simplifying a little bit, this turns into a cosine x over a sine of x, which is cotangent of x. And that result is something you should pay attention to because it is useful with other derivatives that we're going to see. Until then, let's just use this result once, maybe twice more. If I had something like f of x equaling the natural log of x squared plus a 10, and be aware that the derivative of the natural log, it's the natural log you're going to be dealing with the most often. Not to say you won't take the derivative of other logs, but natural log is definitely going to be the most common. All right. That being said, f prime of x in this case, again, starting on the outside, derivative of natural log is 1 over times, and then we move inside, and derivative on the inside would be a 2x, which can be written as 2x over x squared plus 10. All right. And could I have skipped this step? Could I have gone ahead and put the 2x on top and been finished with the problem? Yes. Once you get comfortable with it, that is perfectly acceptable. Nothing wrong with that at all. Same procedure gets used. You're taking a single derivative or you're taking a second derivative. The derivative of natural log will continue to work in the same exact fashion. Also note, again, this is a point in time where, since we're learning some new derivatives, we need to be on the lookout for any logarithms that this might help us with as far as their integrals are concerned. We're doing derivatives of logarithms, so maybe there's an integral that might come into the picture. All right, so if we looked at f of x equaling a natural log of absolute value of x, then if you think about the way absolute value can be defined, we see that this is the same thing as natural log of x if you have an x that's greater than 0. This is the natural log of the opposite of x if you have an x that's less than 0. If we differentiate this, then what's going to happen is we're going to differentiate it in parts. Now, the derivative of the natural log of x was, as we've already said, the 1 over x, and that is if x is greater than 0. The derivative of natural log of opposite of x would be 1 over opposite of x times the derivative of opposite of x, which is -1. So that would still come out to be, in the end, a 1 over x. All right. Now, what we learn from this, therefore, is a little bit, again, like I was saying, that there's a little bit of an implication here, all right, as far as integration is concerned. And the implication is that the integral of 1 over x dx is going to be equal to the natural log of the absolute value of x plus your constant of integration. It is very common when people integrate the 1 over x to forget the absolute value. But whenever taking derivatives, and especially when taking integrals, we want the most general answer, the most widespread, the most usable answer possible. All right, so as long as you remember that you can't integrate across 0 because your natural log is not defined at 0, natural log of absolute value is not defined at 0, 1 over x is not defined at 0, don't integrate across a 0. But as long as you're not integrating across 0, that is the most general solution for a natural log problem. And if I remember correctly, let's do a share screen here. And let me pull that up. If I remember correctly, I do believe the book remembered that. Here the book shows the derivative of natural log is 1 over. On the next page, it shows it with the u assumed to be a function of x. Here is the derivative of absolute value being the 1 over x. Oh, yep, here the book remembered it. I was not sure if this was here or not, but the integral of 1 over x dx is the natural log of the absolute value. All right, so good. It's there. I couldn't remember if it was in the book or not. Now, a result that we had just a minute ago should now be useful to us in doing yet another integral. We now should be capable of integrating the tan of x dx. That's now doable because of what we learned about the natural log. This can be rewritten as a sine of x over a cosine of x dx. Now that we know the how the natural log differentiates and integrates, and we have our u substitution tool available to us, we can do this problem. I'm going to let u equal cosine of x. That way du will be a negative sine of x dx. Solving for dx will be a du over negative sine of x. Therefore, this integral becomes integral of sine of x over the cosine, which is u, times dx, which is a du over a negative sine x. What's going to happen is the signs will cancel. The negative comes out front. I'm integrating a 1 over u du. Let me write that a little bit better, which is the natural log, absolute value of u, plus a constant of integration, putting back what the u was equal to. That's the opposite of the natural log, the absolute value of cosine of x. And then bringing the negative up, and remembering the cosine of the negative 1 power is 1 over cosine, which is secant. All right, so what we now see is we have an integral for tangent, and it just equals natural log absolute value of secant. And again, I believe, I should read the book in advance. The book remembered to illustrate that. That's good. So now you have a new integration technique, which is good for certain types of trig functions. Our knowledge of logarithms can also be useful in something called logarithmic differentiation. All right, if you have an expression that is going to be complicated to differentiate, logarithms can sometimes be of help. Let's say I had a y equaling a 2x plus 1 to the 5th times an x to the 4th minus 3 to the 6th. These large powers and this product sort of is a hint that logarithmic differentiation might be helpful. So how is logarithmic differentiation achieved? Well, first thing you do is take the log of both sides. You have natural log of y equal natural log of this entire expression. All right, and then you're going to use what you've previously learned about logarithms to break this expression apart. This is going to become natural log of 2x plus 1 to the 5th plus natural log of x to the 4th minus 3 to the 6th. Again, because with logs, a product becomes addition. And then also, powers become coefficients. And now I'm finally ready to take an actual derivative. Differentiate here and differentiate the whole side here with respect to x. Derivative with respect to x here is a y prime over y. I went ahead, instead of saying times, I just went and put that on top. Here I can differentiate a sum with constant coefficients, which is pretty easy. This becomes a 5 over the 2x plus 1 times the derivative of the 2x plus 1 is a 2 plus a 6 over an x to the 4th minus 3 times the derivative of x to the 4th minus 3, which is a 4x to the 3rd. Clean this up a little bit. Y prime over y equals a 10 over 2x plus 1 plus 6 times 4 is a 24 over x cubed, x to the 4th minus 3. And then finally, what we actually wanted all along was not a y prime over y. We just wanted y prime. So y prime would be equal to all of this, the 10 over the 2x plus 1 plus the 24x cubed over x to the fourth minus 3 times, to get the y out of the bottom, I would just multiply off both sides by y. But of course, y, if we go back to the top, is the 2x plus 1 to the fifth times the x to the fourth minus 3 to the sixth. All right, so there is a much easier way to differentiate other than using product rules and power rules and so on and so forth. All right, and it gives it to you in at least a semi-factored form, which is often, factored form is often what we want in a derivative. So again, using your properties of logarithms allows you to simplify derivatives on occasion.